Hello, my name is Maria Jose Morales, and this is my lecture from the 2020 Honors Chemistry Short Lecture Series. Have any of you ever heard of Mac Miller? What about Juice WRLD? You wouldn't believe how many entertainers die from the seemingly routine recreational use of drugs. A powerful drug called fentanyl takes countless lives and harms users, including those two superstars, as well as officers in a drug search that come into contact with it who are unaware that fentanyl is present. I want to take some time to shed light on the importance of fentanyl detection and a method of doing so that will contribute to limiting people's exposure to harm. According to a CNN article that touches on the chemical sensing of fentanyl, detecting it is much less of a hassle than it used to be. In this presentation, I will talk about the inspiring article that I mentioned, the brief history behind how fentanyl came into the country, its licit and illicit uses, its potency and how it affects the brain, and why it has become a major concern in this country. I will then explain the processes that scientists use to detect it in the past. Lastly, I will talk about the new method and why it is better for detecting fentanyl, how it is prepared, the different components of the experiment, the instrumentation that is used for the detection, and finally, the results of the detection itself and how scientists know when fentanyl is present. The article that inspired this presentation is titled New Method for Field Detection of Fentanyl. It explains the method produced by Joseph Wang that would apply electrochemistry to detect fentanyl using carbon and polyethylene tetraphthalate sheets with ionic liquid on them. These strips are meant to sense fentanyl in a smaller amount of time for a few cents apiece. Now, for background, fentanyl was first developed in 1959 by a company called Janssen Pharmaceutica, which is now owned by Johnson & Johnson. It was initially intended to be used for cancer patients and patients suffering from chronic pain. What is fentanyl? Here you can see its structure and its different uses. It is known as a lipophilic agonist of the phenylpiperidine subclass of opioids. This means that it combines with fats and initiates a physical response in the body. Phenylpiperidine is a label put on opioids with analgesic and anesthetic properties, meaning that they contribute to the loss of sensation or pain. They relieve pain by activating the mu receptors in the central nervous system that are responsible for the pain-relieving effects of opioids, as well as their other side effects, including dizziness, nausea, and respiratory depression. Fentanyl is also a famous narcotic that, when mixed with other drugs, including cocaine and heroin, increases the euphoric effect. This also contributes to the increase in the profits of drug dealers, as putting more fentanyl in a mixture calls for less of the other drug to be put into that mixture. This is because of fentanyl's potency. A small amount of fentanyl has the same effect as a much larger amount of other drugs. Fentanyl is 50 times more potent than heroin and 100 times more potent than morphine. This means that a milligram of fentanyl would have the same effect as 50 milligrams of heroin and 100 milligrams of morphine. Here you can see the lethal amount of fentanyl in heroin. That of fentanyl is significantly less than that of heroin. Fentanyl is particularly effective because it binds to the opioid mu receptors mentioned earlier more tightly than any other opioid. This causes a stronger and longer-lasting effect on the areas of the brain that control processes like breathing and has a calming effect over the individual that takes it. With this great potency and effect on the brain, fentanyl has become a major concern in the United States. In September of 2019, 47% of overdose deaths were due to fentanyl, and as these numbers continue to increase in the country, fentanyl remains practically undetectable to the human eye, as such small traces of it are used to lace street drugs. A study from a harm reduction journal showed that 73% of the people that tested positive were unaware that they had taken fentanyl. This is because it is very common for dealers to lace their drugs without notifying the consumer. Because this problem has been occurring for some time now, scientists have developed forms of detection used in the past. One of these is thermal disruption direct analysis in real-time mass spectrometry, or TD-DART-MS. This process includes using heat to increase the volatility of the substances, or the ability for them to evaporate. Scientists then ionize the mixture and simplify the structures by causing them to separate into their individual ions. They can then analyze them and categorize those ions to determine the sample's composition. This method allows scientists to compare the exact structures of the mixture of fentanyl and non-fentanyl and compare them to distinguish the fentanyl from the other substances in the mixture. Another example of a traditional form of detection is ion mobility spectrometry, or IMS. It also involves ionization of a mixture. But this analytical technique separates the ionized molecules in the gas phase and compares the substances based on the mobility of the ions. The problem with these two types of spectrometry is that they both require immobile instrumentation found in a lab. This means that by the time it reaches the lab, it would already have been handled by a number of people that were unaware about the fentanyl in the mixture. The next method is called cyclic voltammetry. It starts with the oxidation or reduction of the mixture. This means that scientists cause the atoms in the substances to lose or gain an electron in a chemical reaction. Scientists then apply a voltage and use an electromagnetic scanner to determine the electrochemical oxidation peak potentials and compare them to known behaviors of fentanyl. In this graph, the oxidation peak levels of fentanyl, heroin, and cocaine are compared. Fentanyl appears to have the highest peak point. However, the problem with this process is that peaks often overlap, and it becomes hard to distinguish between the substances. The last form of detection is liquid chromatography. This is something that we should be familiar with. It basically consists of a mixture of fentanyl and non-fentanyl being separated through the application of a liquid. The process consists of a stationary phase, usually a strip or printed material that does not move, a mobile phase, which is the liquid applied, that moves across the strip, and the substances that are separated based on their attraction to the liquid and the strip. This process proved to be too time-consuming. The new method that was produced minimizes all of the flaws of the other traditional forms of detection. It consists of disposable strips that take only 40 seconds to accumulate fentanyl on them and 60 seconds total to detect fentanyl that only cost a few cents apiece, thus making this process time-efficient and cost-effective. Before separating them, the fentanyl and non-fentanyl were prepared. They were each supplied in methanol, the simplest alcohol, that is used as a solvent and consists of a methyl group linked to a hydroxyl group, as you can see in the diagram of its structure here. The fentanyl was diluted, or weakened in force, to 500 micromolarity. This is a unit of measurement that we might not have seen before. It measures molar concentration, or the moles of solute per liter of solution. In this case, there are 1 million micromolarity in a molarity. So there are 500 million moles of fentanyl per liter of the phosphate buffer and fentanyl solution. The fentanyl is diluted with a phosphate buffer, a water-based salt solution made up of disodium hydrogen phosphate and sodium chloride. It has a 0.1 molarity and maintains a pH level of 7.4 Hz. pH stands for potential hydrogen, and it labels whether a substance is acidic or basic. Considering the pH level is greater than 7, the phosphate buffer is basic. Similarly, the non-fentanyl is reconstituted, or returned to liquid state, to 1 mg per milliliter in methanol. This unit of measurement also measures concentration. It can be simplified by saying that there is 1 mg of non-fentanyl dissolved in a milliliter of methanol. The non-fentanyl was also diluted in the phosphate buffer to 500 micromolarity. The next step taken by the scientists conducting the process is the preparation of the ionic liquid. Its chemical name is 1-butyl-1-methyl-pyrrolidinium bistrifluoromethylsulfonylamide, or C4C1-pyr NTF2. Its structure can be seen here, and, for reference, the picture at right depicts a sample 5 times larger than that of which was used in this experiment. Only 1 micrometer of liquid was applied to the strips mentioned. To prepare this liquid, it was washed twice with hexane and treated with activated charcoal, a fine black powder made of bone char, coconut shells, petroleum coke, coal, olive pits, or sawdust. The charcoal is activated when it is processed at very high temperatures. After all of this, the charcoal is filtered out with filter paper and PTFE filters with a width of 0.2 micrometers. PTFE stands for polytetrafluoroethylene, a vinyl polymer from the monomer tetrafluoroethylene. The ionic liquid was also diluted to 0.1% volume per volume in methanol. This unit of measurement is used when both chemicals in a solution are liquid. It can be said 0.1% milliliters of ionic liquid per milliliter of methanol. The reasons behind using this ionic liquid include the fact that it is a hydrophobic ionic liquid. This means that it repels water and allows for wider electrochemical windows to be applied, as it minimizes the entrance of water to the electrode surface of the strips that the liquid will be applied to. The term windows is used to describe the voltage range between which the substance is neither oxidized nor reduced. The ionic liquid also enhances the performance of the electrochemical sensors that will be used to detect fentanyl to get the results of its presence. Now, more specifically, the cation, or the positively charged ion, C4C1 Py+, is a large and bulky. This results in a large ionic liquid electrode interface. Interface is when the surface forms a common boundary. In this case, the boundary would be formed between the ionic liquid and the electrode. Lastly, the cation is also asymmetrical and non-planar. This provides larger cavities that help the fentanyl adhere to the surface that the liquid is applied to. Scientists then make the strips that the ionic liquid is to be applied to. These strips are made of carbon and silver-silver chloride electrodes, printed onto polyethylene terephthalate. That is the chemical name for polyester, and, for reference, is commonly used to make items like food packaging. Its structure is seen here. The carbon ink was used to print the working electrode, the system on which the reaction occurs. On this strip, it is the black line on the right. It was also used to print the counter electrode, that is used to close the circuit without participating in the reaction. On the strip, it is the black circle in the center. The silver-silver chloride was the reference electrode that completed the circuit and maintains a constant potential, like the ones discussed in cyclic voltammetry. On the strip, it is the white line on the left. The polyester was the underlying surface that all of this was printed on, known as the substrate. After putting the sample of the fentanyl mixed with non-fentanyl onto the strips and adding 1 micrometer of the ionic liquid onto it, the fentanyl accumulated on the surface of the strip. It was then scanned by a handheld electrochemical analyzer that was synced to a computer with a PalmSense MStat program installed to it. This is an example of what that program looks like. After oxidizing and applying a voltage to the fentanyl mixture, the scanner was set to certain parameters to apply cyclic voltammetry as well as cyclic square wave voltammetry, which follows the same concept but is used for smaller concentrations, and the waves appear in a different shape. The parameter set on CV includes 100 microliters of the phosphate buffer covering the 3 electrode systems, working, counter, and reference. The machine was also set to a step potential of 0.005 volts. This describes the intervals of which the voltage increases. The scan rate was set to 50 millivolts per second. The scan rate is used to label the average amount of time that each voltage lasts. With CSWV, the amplitude, the increments of which the voltage increases, was set to 0.05 volts. The step potential was set to 0.004 volts, and the frequency was set to 25 Hz. The frequency labels the level that electrical noise, generated by the alternating current voltage applied, is filtered out. Here we see the results of the scan. The black waves are the fentanyl, and the red are the non-fentanyl. The CV, shown at the top, and CSWV below it, were used to identify the fingerprints of fentanyl in the scan. The oxidation peak, at positive 0.560 volts, labeled A1 on the CV scan, is the first anodic scan. This is the same for CSWV scan. The placement of this peak, along with the fact that the peak potentials in the CSWV scan are higher, indicated the presence of fentanyl, as this is a common behavior in oxidized fentanyl. In conclusion, fentanyl is a dangerous drug that can cause harm to anyone that handles it, especially if they do so unknowingly. This new method of chemical sensing through electrochemistry is the best form of detection, as it minimizes the harm in handling fentanyl by notifying those in contact with it of its presence during a drug search. Implicating this in the future has been suggested to law enforcement in the form of a polyester sleeve to be worn by an officer, so that they may always have it on hand. These strips will make handling drugs much safer, as officers can now be aware of the presence of fentanyl and can move forward with the proper procedures when handling it. These are the sites I used to gather information for this presentation. Thank you for listening. I look forward to your questions.